Right now, somewhere out in the darkness beyond our atmosphere, a massive chunk of rock is racing toward Earth at tens of thousands of miles per hour, and astronomers around the world are watching it with everything they've got. For a moment, some of the sharpest scientific minds on the planet genuinely did not know whether this thing was going to miss us or not. So the question everyone wants answered is simple. Should we actually be worried? Let's start with what just happened, because it is not some distant hypothetical. In early August of 2026, NASA's Jet Propulsion Laboratory confirmed it was tracking a near-Earth asteroid roughly the size of a passenger jet, officially designated 2026 OE1, as it made a close approach to our planet. This object measured somewhere around 180 feet across, large enough that if it ever did strike a populated area, it would cause devastating regional damage. It passed at a distance of about 1.82 million miles, which sounds enormous until you realize that in cosmic terms, that is barely more than 7 times farther away than the moon. NASA's tracking systems confirmed there was zero danger, but the fact that an object this large can sneak into our neighborhood and require official monitoring is exactly the kind of thing that keeps planetary defense scientists awake at night. In 2026, OE1 was not even the closest call of the year. Just months earlier, in May of 2026, an asteroid called 2026 JH2 was discovered by astronomers at the Mount Lemmon survey in Arizona, and within just 8 days of being spotted for the very first time, it swept past Earth at a jaw-dropping distance of only about 56,000 miles. To put that in perspective, that is less than a quarter of the distance between Earth and the Moon, closer than some communication satellites orbit our planet. This asteroid measured somewhere between 50 and 115 feet wide, roughly the length of a basketball court, and it circles the Sun once every 3.7 years on a highly elliptical path that stretches all the way out toward the orbit of Jupiter before swinging back in toward the inner solar system. And it was moving fast enough that if it had been on a collision course, there would have been almost no time to react. Scientists were candid about the uncertainty involved. Because the object was found so recently, its orbit could not be pinned down with total precision, and experts openly admitted that our planetary radar capabilities are currently degraded, since the massive Arecibo telescope collapsed years ago, and NASA's Goldstone antenna has been down for extended repairs. In other words, one of our best tools for precisely tracking incoming space rocks has been sitting offline exactly when we might need it most. If a story like this makes you want to know what's really out there watching over us, make sure you like and subscribe. Because the next part of this story got a lot scarier before it got safer. Now let's talk about the asteroid that actually terrified the scientific community, because this one was not a surprise flyby. It was a slow-motion nightmare that played out over more than a year. In December of 2024, an automated sky survey called Atlas discovered a new near-Earth object roughly 174 to 220 feet wide, about the size of a 10-story building. It was given the name 2024 YR4, and almost immediately, something alarming started happening. As astronomers gathered more observations and refined its orbit, the probability of this asteroid actually striking Earth on December 22nd of 2032 kept climbing instead of shrinking. It went from just over 1% to 2.6% to a staggering 3.1%, the highest impact probability ever recorded, for an object of its size in the history of modern astronomy. Headlines around the world began calling it the city killer asteroid, and for good reason, since scientists calculated that a direct impact could release energy equivalent to between 2 and 30 megatons of TNT, enough to flatten an area up to 80 kilometers wide, roughly 50 miles across. For a few tense days in February of 2025, this was not science fiction. It was a live, escalating planetary threat being tracked in real time by space agencies across the globe. Then, almost as quickly as the probability had climbed, it began to collapse. Just one day after reaching that record, 3.1%, new overnight data pulled the number down to 1.5%. Within weeks, additional observations from ground telescopes and eventually the James Webb Space Telescope shrank the uncertainty region around the asteroid's possible path so dramatically that Earth was essentially pushed out of the danger zone entirely. By the following year, the impact probability had crashed to a functionally meaningless 0.001%. And the European Space Agency officially downgraded the object from a level 3 threat all the way down to a level 0. On the Torino Impact Hazard Scale, the same scale used to communicate asteroid risk to the public. But here's the twist almost nobody talks about. As the Earth impact risk vanished, scientists noticed something else, a real measurable chance that 2024 YR4 could instead strike the Moon on that very same date in December of 2032. That probability actually climbed as high as 4.3% at one point, based on Monte Carlo simulations run using the most precise orbital data available. Using fresh infrared observations from the James Webb Space Telescope, captured in February of 2026, NASA's Center for Near-Earth Object Studies eventually ruled out even that lunar impact, closing the book on one of the most dramatic asteroid scares in recorded history. If a rock like this had struck the lunar surface, it would have been visible from Earth in real time, an explosion witnessed by billions of people looking up at the night sky. So why did the probability of impact rise before it fell instead of just shrinking smoothly toward zero from the very first observation? This is actually one of the most fascinating and least understood parts of asteroid tracking, and it happens with almost every single newly discovered near-Earth object. When astronomers first spot something, they only have a tiny handful of observations to work with, which means there's a wide, blurry zone of uncertainty representing every possible path the asteroid could take. Early on, Earth sits somewhere inside that broad uncertainty zone, giving a small, non-zero chance of impact. As more observations come in over the following days and weeks, that uncertainty zone shrinks and tightens, almost like a blurry photograph, slowly coming into focus. If Earth happens to stay within the shrinking zone as it tightens, the probability climbs. But eventually, as the picture becomes sharp enough, our planet almost always ends up outside that final narrow band of possible outcomes, and the risk collapses to zero in what scientists describe as an expected and completely normal pattern, not a sign that something is going wrong. It also helps to understand exactly how these objects get found in the first place, because the process is far more fragile than most people assume. Most near-Earth asteroids are first spotted by wide-field robotic telescopes scanning huge swaths of the night sky. Systems like ATLAS, the Catalina Sky Survey, and the Pan-STARRS network, all quietly photographing the same patches of space over and over night after night, waiting for a faint point of light to shift position against the background stars. When software flags a moving object, human astronomers and automated risk assessment systems, including NASA's Sentry system and the European Space Agency's Aegis system, immediately begin calculating every possible orbit that fits the handful of available data points. The problem is timing. An asteroid only becomes visible to these telescopes once it reflects enough sunlight to stand out, which for smaller, darker objects often means it isn't discovered until it is already frighteningly close, sometimes just days or even hours before its closest approach. Larger asteroids, the kind capable of true regional or global devastation, are easier to spot from much farther away, which is genuinely reassuring. But it also means the medium-sized objects, the ones large enough to level a city, yet small enough to stay hidden until the last moment, represent the most dangerous blind spot in our current detection network. This is precisely why space agencies have started taking planetary defense seriously as an actual engineering discipline rather than a theoretical concern. In 2022, NASA successfully slammed a refrigerator-sized spacecraft directly into a small asteroid moonlet called Dimorphos, in a mission called DART, deliberately altering its orbital period around its parent asteroid by more than half an hour. It was the first time in human history that our species had intentionally changed the motion of a celestial object, proving that if we ever do find a genuinely threatening asteroid with enough advance warning, we nudging it off a collision course. That advance warning is the entire key. Every expert in planetary defense agrees on the same basic principle. The earlier a dangerous object is identified, the smaller the nudge required to save the planet, since even a tiny change in velocity, applied years in advance, compounds into a massive shift in position by the time the asteroid would have reached Earth. Understanding this pattern matters, because there is a genuinely enormous asteroid already on the calendar, and this one is not going away with better telescopes, because we already know exactly where it's headed. Its name is Apophis, and it measures approximately 1,200 feet across, more than 10 times larger than 2024 YR4 ever was. On April 13th of 2029, Apophis will pass Earth at a distance of roughly 20,000 miles, closer than many of our own communication satellites, a close approach so rare that astronomers say an object this size, passing this near to our planet, happens only once every few thousand years. Unlike every uncertain flyby we've discussed so far, scientists are not worried about Apophis hitting us. Its orbit has been calculated with extreme precision, and a collision has been completely ruled out. Instead, researchers are thrilled because for a few unforgettable hours, this massive asteroid will actually be visible to the naked eye from Europe, Africa, and parts of the Middle East, drifting silently across the night sky in full view of anyone who simply looks up. NASA is even sending a spacecraft, the OSIRIS-APEX probe, to rendezvous with Apophis shortly after its flyby, studying exactly how a close encounter with Earth's gravity reshapes an asteroid's orbit and physical structure in real time. It's also worth remembering that near misses are not some rare, modern phenomenon invented by 24-hour news cycles and viral social media posts. Earth has been getting grazed by space rocks constantly throughout its entire history, most of them small enough to burn up harmlessly in the atmosphere as nothing more than a bright streak of light. NASA has stated plainly that objects smaller than about 25 feet across almost always disintegrate before ever reaching the ground, producing spectacular fireballs but little to no actual damage. The genuine wake-up call for planetary defense came back in February of 2013, when a meteor, roughly 65 feet wide, entered the atmosphere over Chelyabinsk, Russia, completely undetected in advance, exploding with a force estimated at around 500 kilotons and shattering windows across 6 cities, injuring more than 1,000 people, primarily from flying glass. That single event, arriving without a single second of warning, permanently changed how seriously governments and space agencies treat the search for medium-sized near-Earth objects, because it proved that something large enough to injure 1,000 people could still slip through completely unnoticed until the moment it lit up the sky. So should you actually be worried the next time a headline claims a huge asteroid is about to pass Earth? The honest answer is almost always no, and the numbers back that up completely. Thousands of near-Earth objects are tracked continuously by NASA's Center for Near-Earth Object Studies and the European Space Agency's Planetary-Defense Office, using automated systems designed specifically to catch dangerous objects years, or even decades before any real threat could materialize. The overwhelming majority of asteroids that make headlines, even ones that sound terrifying like city killer or skyscraper sized, pass by at distances that are, in cosmic terms, extraordinarily safe. What should genuinely give you pause is not any single asteroid flyby, but the fact that our Detectio-N network still has real, acknowledged weaknesses, aging radar facilities, sitting offline, newly discovered objects giving us only days of warning instead of years, and a monitoring system that, however impressive, is still catching up to the sheer number of undiscovered rocks quietly drifting through our solar neighborhood. The asteroids we know about are almost never the ones to fear. It's the ones we haven't found yet that keep planetary defense scientists checking their monitors every single day. There's also real reason for optimism baked into all of this, because the technology dedicated to finding these objects keeps improving every single year. New observatories coming online in the next few years, including next-generation survey telescopes designed specifically to hunt for near-Earth objects, are expected to detect dangerous asteroids years or even decades earlier than our current systems typically manage. Space agencies around the world have also begun formally coordinating through the International Asteroid Warning Network, sharing data in real time so that a discovery made by a single observatory in Chile or Arizona can be verified, refined, and communicated to the entire planet within hours rather than days. The story of 2024 YR4 actually proves the system works exactly as intended. A genuinely uncertain, genuinely alarming object was caught early, tracked with increasing precision over more than a year, and ultimately ruled completely safe using nothing but patient, methodical observation and some of the most powerful telescopes ever built. That is not a story of narrowly dodging disaster through luck. That is a story of a global scientific effort functioning exactly the way it was designed to, quietly protecting a planet that, for the most part, has no idea just how closely it's being watched.